All right. So, welcome back. Let's talk about regression inference today. A few announcements. So, this is just kind of typical announcements, nothing too special this week. So, we have Vitamin 34 due Wednesday, Homework 11 due Friday, and Project 3 Checkpoint also due Friday. So, kind of pretty standard there. And then today's lecture is going to basically be wrapping up this kind of the last 5 lectures, really. We've been talking about regression and sort of building it up. So introduced association and correlation. So we like define what correlation is. And then we went over how do we actually kind of plot two variables together, and then actually see how we can predict a numerical variable given another numerical variable that we have. And then we talked about how we can actually find the best fit line using these squares. And so that helps us fit a line through kind of the scatter plot of two different numerical variables. And then finally on Friday, we talked about how can we look at the mistakes of the line and how the line does relative to the actual data that's there. So again, the basic setup that we have here is we've sampled some individuals. We observe two different numerical variables about them that we think are interesting and maybe are correlated. And so we fit this regression line through the scatter plot of those two numerical variables. And the idea is going forward, if we want to make any prediction on some new individual that we haven't seen, we would just pick a point on the line that corresponds to their value of the numerical variable on the x-axis. Because typically you know at least one of the variables about them, and you're trying to predict some other variable that you don't know the value of. And so the idea is you're just going to pick a point on the line, and residuals let you understand, okay, if we actually did that process for the individuals in our data set, how off is the line going to be from what actually happened? So that's essentially what a residual is. Um, and then today we're just going to talk about, just kind of wrap up that part and then go into actually hypothesis testing using regression lines, which can be pretty cool. Um, so first of all, just kind of a quick recap of what we talked about towards the end of the lecture on Friday. We talked about this variance decomposition, and the way we arrived at the decomposition was we said, okay, well, we know that your y variable equals the fitted values, which is kind of the values on the line, plus residuals, which is basically what's the difference between the actual value and the fitted value. Um, and so you can kind of break up what y is using this. And so we said because y equals these two things added together, you might think that the standard deviation of y equals the standard deviation of each one added, but that's not actually how standard deviation typically works. But we can say that for variance in this case. So in this case, we know that the variance of y, which is like what's the variability of all of the y values in your sample, that's going to be equal to the variability of the fitted values, so the variability of kind of the predicted values on the line, plus the variability of the residuals. So that's kind of the distance from the line of each point. So it turns out the variability of all of those, you can add them up. You have this nice relationship between the two of them. And this actually happens because of the Pythagorean theorem. And so if we know this fact, then there's some other interesting things that we can find out about this that we can use this for. So if we know that this is kind of the relationship with the variances, we've also know that kind of separately, the standard deviation of the fitted values over the standard deviation of y equals the correlation. So we talked about that last time, that relationship there. And so if you just take that equation and square it, you get this equation. So you get the variance of the fitted values over the variance of y is r squared. And so if you just look at kind of this relationship here and the equation that we have above, if you divide the equation above by variance of y everywhere, then on the left side, you're going to get variance of y divided by variance of y. That's just 1. This second term here is going to become variance of fitted values over variance of y. Well, that's just r squared right here. So basically, we could put r squared up here. And then the last, on the right side, you're going to have variance of residuals over variance of y. And so if you solve for this thing on the right, then you're going to basically get that variance of residuals over variance of y is actually 1 minus r squared. So basically just move this variance of fitted values to the other side, subtract it from both sides, and then divide the entire equation by variance of y. That's how you can get this result here. And so this is just kind of another interesting property that there's some relationship basically here. So it's just kind of cool that the variance of the fitted values over the variance of y, that's actually r squared. And then the variance of the residuals over the variance of y is actually 1 minus r squared. And so this can be pretty helpful. And this is going to be true for like any scatter plot that you fit a line through. So it's a very kind of interesting and useful fact. And again, just to clarify, R is the correlation coefficient. So that's that calculation that we talked about last week and defined. And so just kind of taking the square root of those two equations, you basically get something like this. So this is the same thing as the previous slide, but just square rooting these two equations here. So the ST of the fit values over the ST of y equals the absolute value of the correlation coefficient, and then the ST of the residuals over the ST of y equals the square root of 1 minus the correlation squared. So again, this is just kind of natural extension from the previous slide. And then if we kind of, if we focus just on the second part here, so the residuals part, if we multiply the ST of y to the other side, then we can solve for what the ST of the residuals must be relative to the ST of y. And this is interesting because the residuals themselves, you could think of them almost as having like a distribution too. And the way the residuals are distributed is they're always going to have an average of 0, because on average, your residual is going to be 0, basically meaning that like on average, your prediction of the line is going to be correct, but it's not, you know, it's not going to exactly equal the points. Sometimes the actual values are going to be above the line. Sometimes it's going to be below the line, but on average, it's going to be like 0. That difference between the actual value and the line, that's kind of like why the line works. And then the standard deviation of the residuals, so that's like how far you are above or below the line on average. You're typically, the ST is going to be square root of 1 minus r squared times ST of y. So this is just using kind of the same formula from the previous slide. So this is just an interesting kind of property about residuals. And what's cool about this is you could know this kind of beforehand without even looking at the plot of all of the y values and like comparing it to the regression line. You already know what the ST of the residuals is going to be beforehand if you just know the ST of y. So like what's the variation of the y variable and what's the correlation coefficient. So if you can just calculate those things beforehand, you basically already know what the distribution of the residuals is going to look like. Which is pretty useful because you can basically know kind of before you even fit the line, you already know what to expect in terms of like how far the points are going to be from the line. And that's useful because when you're making predictions, you're going to pick a point on the line when you're making a prediction of somebody in the future. But if you have a sense of like what the variability is going to be of that prediction and basically like how far the prediction is going to be from the actual values, then that's useful to know beforehand. And so we can try to combine these things together with this discussion question. So let's say we know that we're trying to predict a final score from a midterm score. And so we know that the midterm has an average of 70, ST of 10. The final, let's say, has an average of 60, ST of 15. And we know that the correlation coefficient is 0.6. So if we know these things, what must the ST of the residuals be? So just kind of using some of the equations we've just looking at, what must the ST of the residuals be? So take a couple minutes to try to think through how to answer that question using some of the formulas we just talked about. Cool. So a lot of people are saying 12. Anybody who said 12, do you want to explain how you got that number? You could just type it out. Yeah, there you go. So basically we're going to use the formula where we know that the ST of the residuals equals the square root of 1 minus r squared times the ST of y. So first of all, r is 0.6. So r squared is going to be 0.36. We do 1 minus that gives us 0.64. And then we take the square root of that. So that's going to be 0.8. And then, so now we have that first part, which is the square root of 1 minus r squared. That whole thing is going to be 0.8. And then we multiply that by the ST of y. So ST of y in this case is 15 because we're trying to predict the final from the midterm. And so basically just do 15 times 0.8, and that gives you 12. So SD of the residuals is 12. And so what does this actually mean? This means that basically, typically, our actual values of our final scores are going to be 12 away from the regression line prediction on average. That's kind of one way to think about it. It's kind of the average squared, root mean squared deviation. So average kind of deviation is going to be roughly 12. So it's kind of large. It means that basically like your regression line probably isn't going to predict it that closely. You could be off by like 12 or more, but just gives you a sense of like how well can you predict the final given the midterm. And so if this SD the residuals was smaller, that means that your prediction does an even better job. It gets even closer to the actual values on average. But it just kind of gives you that sense. And so one question is, what is y generally? So typically y is just going to be the variable that you're trying to predict from the other variable. So in this case, I mentioned in the beginning that like we're trying to predict the final from the midterm. And it kind of makes sense because like the final comes after the midterm. So that's maybe something you might want to do in the future. Like maybe in the future, you might observe a student, then you know their midterm score, and you might want to try to predict what their final score is going to be. This could be one way to do that. You could fit a regression line to some existing students who we know their final and midterm, and then try to use that to predict like future students' final score from their midterm score. Okay, and then we could do one more discussion question before we move on. So this one's a little bit harder. And so this one's going to ask, same setup. So we have our midterm, we have our final. We're trying to predict the final from the midterm. So exact same set of data. But now we're trying to ask the question, for at least 75% of students, the regression estimate, which is kind of the prediction of the regression line, of the final score based on midterm score, is going to be correct to within how many points? So try to see how maybe you might want to go about this one. And then we'll review it together. Okay, so let's try to go over this one. So first of all, when you see something like at least 75% of the students are going to be within something, what does that kind of remind you of? Like we're trying to make some assumption about at least this much of the data is going to be within something. So that should hopefully make you think of Chebyshev's inequality, because Chebyshev's inequality is kind of the one thing we talked about in the class where like we're able to make some guesses about how much of the data is going to be within some certain amount of the average. And so in this case, within some certain amount of the average, that's basically like saying within some certain amount of the regression line. That's kind of the analogy here. So we use Chebyshev's inequality. And so if you remember, Chebyshev's inequality says that like at least some percent of the data is going to be within 1 minus 1 over z squared. So you choose like z, so and then figure out like how much of the data is going to be within z standard units of your average. So in this case, we don't know what z is, but we know that 75% has to equal 1 minus 1 over z squared. And so the value of z that allows that formula to be equal to 75% is actually 2. So 1 minus 1 over 2 squared, which is 1 minus 1/4. That's 3/4, so 75%. So z needs to equal 2 in order for us to use that formula. So what that basically means is at least 75% of the students are going to be within 2 standard deviations of the residual from the regression line. So now that we know, we need to look for 2 SDs of the residual. And then from the previous discussion question, we know that the SD of the residual is 12. So that means you just need to do 2 times 12. And so we get 24. So 2 people got the 24, and that's how you get to 24. So again, really quickly to recap that, we know that we want at least 75% of students to be within some certain number of points from the regression line. We know that according to Chebyshev's inequality, 75% corresponds to 2 standard deviations. And then when we're saying how far things are from the regression line, that's talking about residuals. So if you want something to be 2 SDs from the regression line, that basically means you want it to be 2 residual like the SD of the residual. That's what we're talking about. And so previous slide, ST residual is 12. So 2 times 12. So that's how we get that. So this is kind of a little bit more difficult question, kind of combines like pretty much everything we've learned so far. So it's a, it's a tough one. And we only have limited time to answer it. So don't worry if you weren't able to get that one. But hopefully the explanation makes sense. I encourage you to kind of try to write it out and show it for yourself that that's the right answer here. Cool. So now let's go to regression models. That's going to be kind of the crux of what we really want to talk about in today's lecture. So the idea here is, again, the setup is we sample some individuals, we observe some variables about them. So there's like some numerical variable, which we call like X, and there's another numerical variable Y that we want to try to maybe predict from X, or at least understand the relationship between X and Y. And so how do we do that? We fit this like least squares regression line through the scatter plot. And then now that we have this line, we can make some other statements about the relationship between these two variables. We can say that this, the slope of the line that goes through these two variables is, some specific value. It has some specific intercept. And then if we wanted to see like a new individual who comes in and we know their X value, but we don't know their Y value, we could use this line to make a prediction. We could just look on the line, see where the line, equals the X value of this person, and then just go up to the line, like that's going to be our prediction for them. So you can make predictions now using this regression line on new individuals that aren't in your sample. But one thing about this is that this sample that we saw, remember, it's random. Every time we take the sample of individuals, we're going to get something slightly different. We're going to get a slightly different scatter plot every single time that we sample new people. And so what that means is that regression line that we're going to determine from our scatter plot is also random. So that regression line itself is essentially an estimate. It's not actually like our true relationship between these two variables. That's just the line that we happen to get with this sample that we happen to get. So every single time we sample those variables, we're going to get a slightly different scatter plot, which means we're going to get a slightly different line every single time. And so that's the basic idea for kind of the rest of this lecture is what does that mean? Why are we getting a different line every time? How do we actually like interpret this? And so we'll just go into that right now. And so the basic idea is we're going to make some assumption about how the world works between these two variables in the population. So we're going to say in the population, there is kind of this true line. There's like some true line that we're never going to actually know, but we want to understand. Just kind of like, we talked about how if you have like a bunch of flights and there's like some true median, but maybe you're never going to know the true median. So you like try to sample and take the median of the sample to guess at the median of the population. Same idea here. There's some true relationship between the two variables, and we're trying to figure out what that relationship is. And what's gonna happen is the way the data is actually generated in the population is that there's some noise there. So not everything in a population just like falls along this line. There's a little bit of variability there. Every individual is different. Everybody has some kind of randomness in them. And so the way that the population is actually created is that you take this line and then you sample a random distance that's drawn at random with an average of 0. So sometimes the distance is going to be above 0, sometimes it's going to be below 0, but on average, the distance is going to be 0. And so that's how we'll create a single point in the population. And then we'll do that again to create another point in the population. And then we'll do that again, and we'll do that again. And so this isn't actually how a population works. This isn't actually how two variables are created in the real world, in the natural world. But this is kind of our statistical model. This is kind of an assumption that we're making about how the data in the world is created. We're going to assume that the data in the world is created using this kind of a framework. So there is a true line, and then things are just randomly drawn above and below the line. And that's how like things are created in the population. And so with that assumption, what's going to happen is this is kind of how we think the world works. And then what we're actually going to observe is just the points. So we don't actually get to see what that line is. We just see the result of that process. We just see the points, the scatter plot. And so our goal is we see these points, but now we want to try to fit a line through them so we can see if maybe we can recover what that true line is in the previous slide. So does that make sense? Any questions about that in terms of like how we're thinking about the world? Like as data scientists, this is essentially like how we're thinking about the world. And it's, it's a pretty strong assumption that we're making here, but that's kind of the idea. Yes, I mentioned the mean must be 0. So all I'm saying here is that like when you have this line and you're like generating points from it, on average, the distance that you're generating is 0. but it's not actually like literally 0, but just because sometimes it's positive, sometimes it's negative. So basically, average is 0. You can think of it meaning like it's equally likely to be above the line than it is to be below the line. And yes, this is assuming there's a linear relationship as well. So like if you have a really strong belief that there's a linear relationship between these two variables, then that's the assumption you're making. So it's a very, very strong assumption. And some of you guys are hinting to what this is going to get to, which is someone said like this is a null assertion or null assumption. So yeah, we'll get to that. But that's kind of the assumption we're making here. And so let's take a look at how we can actually quantify this. So if we go to the demo here, we've made a bunch of functions. A lot of these are like just kind of combining everything we've done in the last few lectures. So there's a function that can like create standard units. It can calculate the correlation, calculate the slope of a set of variables, the intercept, fitted values, and so on. So I won't go too much into those. And then the function we're going to use right now is this function called draw and compare. And so again, for this one, I won't go too much into it, but I'll just run it first so you can see it. But the basic idea, the way it's going to work is it's going to generate a bunch of data for us. And you specify 3 parameters. So you specify what the true slope is, what the true intercept is. So in this case, you're going to have like 2 variables where there's an intercept of -5 and a slope of 2. And then we just choose how much data we want to sample from that. So what this basically is going to do is it's going to do the exact thing I just talked about in that model slide. So it's going to create some theoretical line with an intercept -5, a slope of 2, and then it's going to take that line and then randomly sample 10 points from it. And so we're going to kind of be able to peek behind the curtain and see like everything. So let's actually just run this once, and then it'll make a little bit more sense. So firstly, this first plot, we see kind of the true line. So this green is the true line, and then the blue dots are the 10 randomly sampled dots from this line. And so this function just does it for us. So basically, this is the true line, and then these are the dots that are being kind of randomly generated from the line. And then what do we actually get to see? So if we were actually data scientists in the real world, we wouldn't get to see the green line. We would just see the blue dots. So this is actually what we would get to see. And then once we see the blue dots, what would we do? We would take these blue dots and we'd fit a line through them using the kind of least squares approach that we talked about last week. And so that's going to be our regression line. So you would get, what we would see is we have these blue dots, and then we happen to fit a line through them, and we got this blue line. And then finally, if we were able to peek behind the curtain, we could see how this blue line compares to the true line that points were generated from. So the points were actually generated from this green line. And then this blue line looks a little bit different. And so the natural question is probably, why aren't these lines the same? And the reason for that is because, again, up here, when we generated the data, we randomly drew those blue points. So those blue points are drawn at random. And maybe by chance, you might get a few blue points that are just like, you know, a little bit higher. And so because of that, now the regression line that you fit is a little bit higher as well. And so that's just going to happen by chance. You're not going to typically recover the exact same value. And so again, the analogy is really similar to what we've talked about before when we talk about estimating like the mean of a population or the median of a population, right? You're not going to get the exact same value in your sample as you will in the population. And so that's the idea here too. We're just sampling like 10 individuals. It's going to be pretty noisy. So it's going to jump around. 10 people, you could just happen to get like 3 people that are very different. And then all of a sudden your regression estimate is going to be super different. So this is one example of doing this. And so in this case, the blue line was kind of like tilted above the green line. And we could run the same thing again. So if you just call this function again, it's going to sample another 10 people and then see like where they end up. So we can do it again. So this is, again, this green line is the same as before, but now we've sampled again with slightly different points. So this time when we did the sample, we got some like down here by 70. You know, up here, we didn't get any points as low as 70. So this, in this case, we happen to get some like ones that are really far down. And then you also got some that are like way out here. So, you know, the sample is a little bit different. And then again, this is the actual data we would observe. And then if we actually fit a regression line, we'd get a blue line, and then we can compare it to the green line. So in this particular case, turns out the blue line is like almost perfect. It's like really close to the green line. So that just happened by chance though. So you can kind of see there how it kind of changes every single time. And then the idea is if we do a larger sample size, so let's take the exact same line, but then do a sample size of 100, then we would see a lot more points. So now we see way more points here. And then now if we fit a regression line, we get this blue line. And so now we see this blue line and the green line are like really close together. And then what's nice about this is if I run this again with 100 points, so now I get 100 completely different points generated at random. And then now if I do the blue line, again, this blue line is also still like pretty close to the green line. So you're seeing that there's less variability in the regression line that we're creating because we have a larger sample size. And so this, again, same analogy holds to just estimating like the median or the mean of a population. If you have a larger sample size, your estimate's typically going to be less variable. It's going to be closer to kind of the true value. And so that's kind of the basic idea there. Cool. So that's kind of the model framework. And so the next thing you might want to do once you have this idea of like, okay, this is kind of how we're thinking about how the world's data is generated and how we're like trying to fit the value. And so next thing you might want to do is understand what's the variability of our prediction. Just like with estimates, if you're estimating the median, you want to know what's the variability of your estimate. Same thing here. You want to know what's the variability of your predictions, because that's ultimately why you might want to fit a regression line. And so the idea here is if the data comes from a regression model and the sample size is large, then your regression line is going to be close to the true line. And so what that means also is if you take a new value of x and you predict y, you should predict y finding the point on the regression line at that x. And we're going to just show you like how that prediction of a particular value on the regression line, how does that vary as well? So we can take a look at that. So for this exercise, we'll actually take a look at the same data set we've looked at for a while, which is like all the babies and the mothers. So if you recall, we have this data set here. So you have these different properties about each kind of pregnancy. And so we're going to look at basically birth weight and gestational days and look at like how gestational days relates to birth weight. And so here's some kind of like cutoffs for what you should expect in terms of gestational days, according to the CDC. And so let's actually take a look at a scatter plot of the actual babies that were born. So if you look at the actual scatter plots, we see the gestational days here on the x-axis, and then you have the birth weight on the y-axis. So seems like there's some sort of correlation there. I mean, it almost looks like a vertical line, but it is tilted a little bit. So certainly seems like there's some sort of relationship here. And so there are a couple outliers. That's one issue with this. So we have like a few points out here, which didn't have many gestational days, but they had like a birth weight, which is like pretty standard. So what I think what we'll do is we'll just kind of remove some of those outliers. So we're just going to keep the people where the gestational days was between 225, like around here, and 325, which is around here. So that'll help us kind of just remove some of these outliers. So let's do that first, and then let's look at that scatter plot. And so now we have the scatter plot kind of more zoomed in because we've taken out the outliers. And so you can see this correlation a little bit better here. So it certainly seems like there's some sort of relationship going on. And so let's actually fit a regression line through this scatter plot. And so this is kind of the line that we get based on this particular sample. And then let's also just like take a look at the correlation as well. So in this case, we have a correlation of 0.4229. Yeah, some people said he thought the line was going to be steeper. I kind of thought that too. But it mainly doesn't, it's not that steep because you have a lot of these points out here on the left and the right. So these points on the left and the right kind of bring the line down a little bit. If you didn't have like the cloud of points over here on the left and over here on the right, then it probably would have been a little bit steeper. It's also a little bit hard to tell because a lot of points here are drawn on top of each other. And so you can't really tell exactly like how the points are distributed. Like the points could be all like clumped like this rather than like this. It's a little bit hard to tell. Like the overall shape looks like that, but points could actually be just like this. So a little bit difficult to see because of the overlapping of all the points. So in any case, so we have the correlation, and then we're also going to use this function here called prediction at. And so this will just allow us to take, you basically input the entire scatter plot, and then you also input what the x value is that you want to predict at. So this is kind of like, we have our sample of babies. Let's say there's a new baby that comes in. We know what their, how many gestational days they have. What do we think their birth weight is going to be? So that's how we could do a prediction on a new baby, essentially. And so this x value would be the gestational days that you would pass in. And then it's going to return kind of the prediction of the regression line. So if you look at this function, it basically just does like what the regression line, what you would expect. So takes the slope, multiplies it by the x value, and then adds the intercept. So just kind of plugging it into the regression line, essentially what it's doing. And so let's try like prediction at a specific value. So we can do, for example, prediction at 300. I know it says 287. It should be 300. So let's run this. So prediction at 300 is going to be 130 in this particular case. So if we go up here, what that means is if we have a new baby come in and we know they're 300 gestational days, then our prediction for their weight is going to be whatever the line says at 300. And in this case, it's basically telling us the line says 130.8, so slightly over 130 ounces. And then we can also visualize this too. So if we just put it all together, basically what we're saying is if you have a new baby come in and they're at 300 gestational days, then our prediction is going to be basically just take 300 and just shoot it up to the line. And that's going to be the prediction. So that's going to be corresponding to about 130, 131 roughly. So this is how we can make predictions using the regression line. And then one thing we're going to do here now is look at kind of the variability of the prediction. So let me just run this. So you don't have to worry too much about what this code is doing in detail, but essentially what this code is doing is it's kind of give us a sense of understand the variability of that prediction. Because again, here we had this particular sample of babies that we happen to see, and we fit a regression line through it, and then we made a prediction of some particular individual. In this case, individual with gestational days of 300. So we made a prediction using our particular regression line. But I just mentioned earlier that this sample that we're seeing, it's random. So there is some randomness there, there's variability there. So every single time we take another sample from the population of a bunch of babies, we're going to get a slightly different scatter plot, and we're going to get a slightly different regression. And so the idea is, if you were to tell somebody, like let's say, a mom came in, she's at 300 gestational days, you're trying to understand what the birth rate of the baby is probably going to be. You may not want to just give one answer. You might want to be able to give a range. You might want to say, okay, 131 is our best guess, but it could be within this range, right? And so if I wanted to give a range, a confidence interval, something like that around that prediction, how could I do that? Well, one thing I could do is I could go to the population and then like sample a bunch of babies again, and then fit a regression line to them, and then do that process like thousands of times. But that's pretty expensive to sample people. So what we're going to do is exactly what somebody just suggested, is Bootstrap. So we have this sample, we have a lot of people. Let's just do bootstrapping. Let's just resample from it. And then we'll just kind of resample the scatter plot, fit a regression line, resample the scatter plot, fit a regression line, and just keep doing that like 1,000 times. And then that can give us a sense of how this regression line moves around, which will then give us a sense of how does our prediction for this person move around as well. And then that allows us to create a confidence interval. So that's essentially what we're going to do here. And so this line of code here is basically going to do just that in a few steps. So firstly, we have our original sample here. And if we resample using bootstrapping, we come up with a few different samples here. So these are just like, I think it goes, yeah, just 5 other examples of it. So you can see it's not exactly the same. I mean, they look really similar though, but it's not exactly the same. And you can verify that. So for example, here, like in this blue one, the original sample, you have these like 2 dots right on top of each other. You don't have that in sample 1 or sample 2 or sample 3. So you can just see like it changes around a little bit. These 3 dots here happen to be sampled again in the Bootstrap sample. So, some of these points are going to look the same, but some of them aren't. But this is the basic idea here is every single time we're like resampling from this sample that we have, we're going to have a slightly different scatter plot that we see. And that's going to allow us to assess the variability of our prediction. So that's kind of the idea of bootstrapping your entire sample, or your entire scatter plot rather. And then once you do that, then the next thing would be to actually fit a regression line and then look at what the prediction is going to be each time. So here we're going to see 4 scatter plots that are kind of resampled from our sample. And then for each one, we're going to fit a regression line and then make a prediction at 300. So in this particular case, this first one, we resampled, fit a regression line, and then at 300, our prediction was 132. So a little bit higher than the first time. Then we did it again, and then we got something slightly lower. In this second case, we got 130.8, which is like almost spot on to the original sample. Did it again, got 131.8. Did it again, got a little bit lower, 129.6. So these numbers are probably a little bit more helpful to look at because these scatter plots look like almost the same. You can't really like see the difference here in these lines, but these lines are different. So all four of these plots here have a slightly different line. And again, why do they have that? Because they have a slightly different scatter plot. So if you resample the data, we have a slightly different line every time. And so it might be helpful to try to see these like a little bit closer. So here is doing 10 times. So doing the same process, but 10 times of creating like 10 different lines. And this is just showing the lines on top of each other. So I think this one's a little bit easier to look at than the other one. But basically we're just taking like 10 different bootstraps, calculate the regression line on each of them, and then now let's just like stick all the lines on top of each other. So much easier to like visualize, basically. And so you can see here like how much the line moves around. So you can see like sometimes it just kind of jumps around a little bit based on whatever data we're getting. And so these dots here are corresponding to what the prediction is at 300. And so you can see kind of how the prediction is varying. So it's not varying that much, actually. It's like typically around 130, which is what our original sample got. But you can see that it jumps around a little bit. That's the basic idea. Cool. So this is kind of giving you a sense of how the line moves around a little bit. And then finally, we can go here and we can see the actual kind of how all of these things vary. So this is the same set of lines, but now we can actually see kind of what's the slope and intercept in each one. So this is like if you do it 10 times, you can see like how the slope varies. So sometimes the slope is as low as like 0.5, sometimes it's going to be as high as 0.6. The intercept varies quite a bit. So sometimes it's like -24, sometimes it's as high, or I guess as low as -49. But what's interesting is these predictions don't change that much. 300 is typically around 130-ish. The prediction at 291 is typically around 125, 126. The prediction for somebody who has like 309 gestational days, that varies a little bit more, but still it's like roughly around like 136. So you can just see how this line is like kind of varying for all the different values. And then lastly, we can actually zoom into the line too. So we're going to do the same thing that I did above, but now I'm just going to zoom into 300 so you can really see like the variability really clearly. And so now we've zoomed in. So now this graph only goes from like 292 to 307. So we're like really, really close to the lines, but you can see how these lines are moving around. And now you can kind of start to see like, okay, now I could maybe create a confidence interval for what the prediction should be for this person who has a gestational days of 300. And so now you could give like an answer that has maybe a little bit more context. You don't want to just give maybe one single number. And so that's kind of the idea. Cool. So that's our regression prediction. That's kind of how it varies. And so finally, if we wanted to make a confidence interval for the prediction, here's how we would do it. Basically what we just did. So bootstrap the scatter plot, which basically means like resample your individuals with replacement. And again, remember, we're talking about two different variables here, but each individual is just one row. So you can just resample the entire table with replacement, and that's going to resample both of those variables as well. And so that's how you can kind of like bootstrap the entire scatter plot. And so you bootstrap the entire scatter plot, like resample the individuals with replacement. Once you do that, then you get a prediction for y at the x value that you care about using the regression line that's fit through that particular resampled plot. And then basically just repeat these two steps many, many times. And then you can create something similar to what we just saw, that kind of zoomed in picture. That's kind of the idea of what you're trying to create there. And then once you've done this like maybe 1,000 times, you probably don't want to draw like 1,000 lines on top of each other. So at that point, what you can do is just take all those like little predicted values and then just make a histogram out of them. And that's going to be kind of the empirical histogram of the predictions. Then you just get the middle 95% interval. And so that's approximately 95% confidence interval for the height of the line, of the true line at y. Because that's really what we're trying to get to. We're trying to get to the height of the true line. Remember that line that's like kind of used to generate the data, that line that we'll never really know, but that we're trying to like figure out what it might be based on our sample. So just kind of running that together. I won't go through this function too much, but this function basically does what we want. So if we just run this, it'll take some time, but it's basically going to go through bootstrap the entire scatter plot, predict the value at 300, and then just like store that value in an array, and then finally plot a histogram. So this then gives us a histogram over like several values. I think we did 1,000 repetitions, yeah. So this is 1,000 bootstrap samples. And so here you can see the histogram of all the predicted values for x equals 300. And then if you wanted to create a 95% confidence interval, just take that middle 95% of the data in the histogram. And so in this particular case, the 95% confidence interval for somebody who has 300 gestational days is going to be between 128.8 and 132.6 ounces. So this is a confidence interval on their birth weight and happens to have a width of 3.8. So it gives you a sense of kind of the variability there. So any questions about this process that we just did? Oh, that's a really good question. Someone said it's kind of weird that the 95% confidence interval is so slim compared to all the data that was there, right? If you go back to the scatter plot, that's a really good question. So if you go to the scatter plot, right, if you look at 300, this data like jumps around a lot. Like you have values as high as like 160, values as low as like 100. So like the confidence or like the interval or 95% of the data in our sample is like really, really varied at 300. But then our prediction at 300 is like really tight. It's just around like 128, 129, 130. So like, how is that? Why is that? So the reason for that is because we have so much data in our sample. So there's a lot of all of these data points here influence our prediction. It's not just the points in this kind of little sliver here. All of the points in our scatter plot influence the regression line. And so because of that, the variability in your scatter plot isn't that high. Every single time you resample from the scatter plot, most of these data points are going to basically be the same because we have such a large sample size. And so that regression line isn't going to change that much. So the variability of the regression line isn't going to be that high. And in general, the variability of the regression line is going to be less than kind of the variability of your data. And that's basically why. It's just because we have so much data in the scatter plot. So the line is kind of pretty solid. It's not going to move around that much. So that's a really cool question. Cool. So now we know how to make confidence intervals for a prediction. What's also interesting is to look at how this kind of varies for different values. So we specifically looked at a value of 300, right? Let's try another value like 210. So that's like going to be way out here on the left. So let's see like how the prediction for 210 varies. And then we'll also see how the prediction for 280, which is like closer to the center, how does that vary? So let's take a look at both of these. I'm just going to run both of them. And you'll see something kind of interesting here. And I'm also going to just run this last cell too. Okay, so if we recall up above, when we did 300, our confidence interval for 300 had a width of 3.8. Now, if you try to do something that's 210, which is like really far left, it's like off of the histogram, then we get a width of 10.79. So it's like 3 times as wide, our confidence interval. So we're like not that confident in our predictions. That's like way out here at 210. That's kind of interesting. And then if you look at 280, which is kind of near the center of the scatter plot, that only has the confidence interval for the prediction at 280 only has a width of 1.89. So it's even smaller than 300. So it's kind of interesting. Basically, what you're seeing is that this confidence interval for your prediction, it varies a lot. It's really large. The width of the interval is really large when the value that you're trying to predict at is really far away from the center of the scatter plot. And then when it's near the center of the scatter plot, then it's like really thin. And it's like really tight around there. And so if you look at the actual mean of our data set, the mean of the y values in our data set, or the x values, sorry, is 279, which is like basically 280. And so that's why we're seeing that this is like so thin. So any thoughts there in terms of like why would we have less variability around the predictions for x values that are like at the center of the scatter plot? And then why would we have such large confidence intervals for x values that are far away from the scatter plot? Yeah, so some people are saying there's a lot more data near the center. I think that's a good intuitive explanation for it. It's not quite the right answer, but it's pretty close. But the actual, I mean, that's like a really good intuitive way of thinking about it though, because you don't have much data out here, and so like every time you resample, the data out here is going to jump around a lot, whereas the data around here isn't going to jump around that much. So to just kind of explain why you have like way more variability on the outside, but the crux of why this happens is because every regression line goes through the center of your data. Every regression line goes through the center of your data. So if you go back to the derivations of how we went through the least squares regressions, you'll see that it's true. And so every time we sample from our data and we fit a regression line, that regression line is going to go through the average of x and the average of y. To create that scatter plot point, average of x, average of y, the regression line has to go through there. That's just by definition, it's going to do that. And so, we're resampling. So obviously every single time we resample, we're going to get a slightly different value of average of x, average of y. But again, when we have a really large sample size, that average isn't going to jump around that much. So every time we bootstrap, the average of our x and y isn't going to change that much. So the variability of that particular point is going to be pretty low. And so that's why almost all of our regression lines are going to go through that point, basically, or really close to that point. Whereas once you're way out on the edges, there's no guarantees there on what's going to happen. And at that point, it's really more just like, what does your data look like? And how does it vary when you sample it? And so that's basically it. But yeah, someone got that. Regression line goes through the mean. So there you go. But yeah, you guys all had like the right kind of intuition there. So that's great. So yeah, we'll kind of go there. And then finally, we'll just talk about, so we just went over this, predictions of different values of x. So basically, since y is correlated with x, the predicted values of y can depend on the value of x. And so the width of the confidence intervals also depends on x. And again, it's lower. Confidence intervals are going to be tighter around the center of the scatter plot because your regression line goes to the mean. Cool. So last thing that I want to talk about is this concept of the true slope. So like, what is the true slope? And we won't ever really know, but the idea is how do we see if we can estimate it, as reliably as possible. And so using the same kind of technique we just did, we could create a confidence interval for the slope. So how do we do this? We would bootstrap the scatter plot, so kind of resample it many, many times, fit a line through each scatter plot, and look at the slope of the regression line through each scatter plot. And then once you have all of these different slopes, then you can draw an empirical histogram of all the slopes and then create a middle 95% interval. And that could be a way to create an approximate 95% interval for the slope of the true line. And so again, you can see like this same kind of theme here, basically. The idea is you're going to bootstrap your data and then do something, create some estimate out of it. And then that allows you to see the variability estimate. So you can do the same thing whether you have like one variable and you're trying to estimate the median of something, or if you have two variables and you're trying to estimate like the variability in the prediction of your regression line, or the variability in the slope of the regression line. You could do this with the intercept as well if you wanted. If you care about, if that's like an interesting property for you, the intercept of this regression line, what's the true intercept? Could do the same thing there as well. But it's basically the same exact idea. And this can be a way to create a 95% confidence interval for the slope of the true line. And this can be really valuable because there's situations where that slope actually means something. There's like something interesting there in terms of like the relationship between these two variables, like how strong, what is that like strength of that relationship? That if that slope is important, there could be a lot of cases where you might want to do this type of thing, and you can create an interval around that. And then the really specific case where this is like super important, so I'll skip the demo because we don't have that much time, but the case where this is super important is if whether you're trying to understand whether two variables even have any relationship whatsoever. And so the basic idea here is, let's say we observed a slope based on our sample of points. So we see some slope that's like not zero. But again, we know that the data that we got is just randomly sampled. And so by chance, we might have happened to sample some data that's like a little bit tilted like this, but it might have just been by chance. And so it might be true that the actual line in the population is flat, like the actual line that generates the population is flat. And so the idea is, how could we assess that, whether that's true? Well, we could do that using the same concept. So we can basically say we had this null hypothesis where the slope of the true line is 0. So by default, we're going to say there's no relationship between these two variables. Our alternative hypothesis is going to say, no, it's not. There actually is some slope that's interesting there. And then how do we actually verify whether that's true? How do we test that hypothesis? Same thing we just did. So we'll construct a Bootstrap confidence interval for the true slope. So we'll kind of resample our data many, many times, fit a bunch of regression lines, and then look at how that slope varies across all of our samples. And then we'll create this kind of 95% confidence interval of the slopes. And then basically, if that interval doesn't contain 0, that means that the data is more consistent with the alternative, that there is an interesting slope. Whereas if the interval does contain 0, that means that the data is more consistent with the null. So like it's probably just by chance that we saw our particular sample, we happened to see like a slope of positive whatever. In our resampling, sometimes we got like negative, sometimes we got whatever. So basically that means it's like basically just noise and it's just random. But that's the basic idea here is you can now use this concept of bootstrapping your scatter plot to actually test whether there is any kind of relationship between your two variables. And this is how you would do that. So sorry, I know I kind of like rushed that last part, but I think we'll stop there and I'll stay on for any questions to clarify any of this.